Hello viewers. Today we discuss about a new concept related to railway system. So in this project, we are going to discuss about the control and energy management of railway systems when it is integrated with the microgrid stations. Okay. Actually, this paper is published by the New York government. So come to the topic. You already know in recent railway system we having a huge microgrid assembling infrastructure. You already know that one. Okay. So when you talk about the assembling of microgrids means there it contains majorly distributed active loads, sources and storage devices. Okay. Majorly we discuss about the railway system. Railway systems means here distributed active loads. Okay. Simply trains, you just call it trains. Trains here act as a distributed active loads. And sources we are focusing on in this model will be photovoltaic panels, wind power system, and batteries. For storing high power inside the train, we are using supercapacitors. So, in this picture, we are observing that here we having smart grid 1, smart grid 2. Like this way, you having a number of smart grids. You already know the role of the smart grid means to generate active power to the loads. Here, the distributed active load means trains we are considering. Inside the trains, that means inside the train engine, we are placing supercapacitors for storing power. Okay. So, smart grid containing photovoltaic systems, wind systems, energy management, and batteries. These are the internal structure of the smart grid one as well as smart grid two. Okay. So, majorly the proposed design focus on the electric train. If you consider electric train, what are the disadvantages with the electric train? The major disadvantage is energy recover during regenerative braking time period. Why? Because if you consider electric motors, the electric motors having main disadvantage. What is the main disadvantage we having? Regenerative braking time period. We need to track the power, energy or power. Okay. So this is the major disadvantage, and also while using supercapacitors, the charging time period of the trains will be large. That is also one disadvantage. Okay. So in order to reduce these overall parameters, we are using energy management control strategy. Okay. The energy management control strategy is mainly used for the low energy transfer, I mean, low burden on the design and also fast charging purpose. For these two purposes, the main control strategy create a major role. So in this model, I will show you in block diagram. You know that the electrical vehicles are simply electrical trains. It started from the charging station one, the speed of that one. In order to increase the, suppose if you just considered particular time period, the trains will consume the energy. The energy consuming by the train will be like this way. A particular time, the capacitors, supercapacitors inside the train, going to store the power, store the energy. Okay. Then in intermediate stations, the train is going to discharge. So this is the regenerative braking time period. Okay. The time into say. So when the braking modes at that time, the supercapacitors are going to charge. So that is an advantage of the proposed design. So this is the overall proposed design. In train configuration, we are using a pack of supercapacitors, buck boost converter, train engine, and also DC bus link. So by pack of supercapacitors is directly connected to the buck boost converter of the transmission lines. That means 25 kV line. Okay, you just consider 25 kV line. And then it is connected to the batteries. And that batteries is connected to the buck boost converter and to the smart grid 1 and 2. In smart grid 1 and 2, we having batteries, photovoltaic panels, and wind energy system. I will show you in Matlab. So this is the train 1 and train 2. This will be act as a distributed active loads, and this will be connected to the smart grid. This is the overall smart grid structure. This one is the smart grid 1 and smart grid 2. In smart grid 1, we have solar panel power generation and wind power generation. And here we are using MPPT controller to boost the PV voltage. And here we are using bidirectional buck boost converter. Okay. So this is the overall constructional diagram of the proposed one. And control strategy using here will be as shown in the energy management control scheme. This one is the block diagram of the energy management scheme. Whatever the control is I proposed here, that is totally depend on this one. Okay. So now move on to the simulation results. In figure number 7, we are observing current, total current induced at the terminals, at the station 1 terminals. Okay. Current, total current induced at the station 1. That means PV and wind current. I will show you here. I just run the model. So I just go through the train model. Inside the train model, what blocks will be exist, I will show you here. So inside the train model, according to the design proposed in this paper, the train model contain train engine. This one is the train engine and DC link voltage. This one is the DC link voltage and buck boost converter, and using pack of supercapacitors. So I am using a pack of supercapacitors here. So I am using pack of means a number of, okay. Why? Because supercapacitors means large rating of the capacitors, right? So a number of capacitors will be connected like this manner in order to create the supercapacitor. And then given to the buck boost converter. So in this design, here buck boost converters plays a major role. Why? Because you already know bidirectional DC-DC converter. Here buck boost converter means bidirectional DC-DC converter. That that means for certain time period it will be act as a charging mode, and particular time period it will be act as discharging mode. So that is the advantage of the bidirectional DC-DC converter. As well as the same similar diagram in train 2. Okay. And also in smart grid 1, in order to generate duty ratio for the boost converter, this is the boost converter, right? This is the boost converter. So in order to create duty ratio, DPV means duty ratio. MPPT controller is here we need to implement. So MPPT controller is this one. So major role of this one is to create duty ratio. Okay. So this is the overall part regarding to the concessional diagram related data. Okay. Now move on to the simulation results. This one is current across the PV individual station 1 with the PV and wind currents. Okay. Second one is DC link voltage across the station 1. That means at this terminal. Okay. And station 2 means this terminal. And also same battery rating across the station 1 and state of charge across the station 1. This is the related diagrams. Okay. Now figure number 8. Here I am using train 1 to station. I am just considering train 1. The charging current of train 1 from the station 1. Okay. And also we need to take charging current of train 1 at different time interval. Okay. Station 1, station 2 and load power across the train. I will show you in simulation diagram. So this is the simulation result for the charging current of the train 1 at the station 1 and station 2. Regarding to with respect to the trains, okay, with respect to the trains, we need to consider the charging currents. So this is the overall structure regarding to that one. Okay, these are the simulation results regarding to the figure number 8 as well as figure number 9. Same parameter when the simulation test is considered at the train 2. Previous time we are considering train 1. Right now we are considering train 2. Same parameters. Okay. So this is the results regarding to that one. Charging currents across the train 1, charging currents across the train 2 with respect to the station 1 and station 2, load load power across the train 2 and VDC terminal voltage across the train 2, state of charge across the train 2. So this is the overall topic regarding to the control and energy management of railway system connected to the microgrid. Thanks for watching this video.